today I took the example from yesterday and I did a more mathematical approach and wrote the actual formula, broke it down, and did kind of an analysis here. The actual problem, I took this video, I don't even know. The links for what I'm doing and like the problems and the actual data science is in the links story. There's a story I have, it's called links, or I believe, if I still have it up, the link tree in my bio, and they both have my Google Drive folder for this stuff. So we start with this data set, right? So we have 6 rows and we have dogs, right? So this is basically the amount of toys each dog has. So the 0th dog has 8 toys, the first dog has 7 toys, another one has 1, 3, and so on. So my objective was to find the standard deviation. So basically how far the data was spread out in terms of the mean. Because if you order it, and you add all the numbers and divide them by how many rows there are, you get the actual mean. So the mean is 5, right? So a low standard deviation would look something like this, because think of it horizontally. Like, I know it's like higher, so how does it make sense if it's low? Because it means that the mean should be around here. So this means that all the data points are actually clustered together, while over here all the data points are spread out. So that's why it's called a high standard deviation, a high deviation. Deviation means spread. So a high spread of data points, while this is a low spread of data points. Okay? So the objective was to find if it's a low deviation or a high deviation. So how far is it, how far spread out is the data points from the mean or the average? Another way we can say this is, what was I gonna say? How far? Yeah, I don't remember what I was gonna say. Okay, so find the standard deviation. So then what I did was, I searched up the formula for standard deviation, and the symbol also, and it's the square root of the sum of the deviation from the mean squared divided by the number of actual values there are in the row, which are 6. So I took the actual formula and then actually personalized it for my problem. So I used color codes, so it's kind of easier to understand. So I started from the inside. So this is our actual value. So those are actual toys. So this could also be our X, if you can think of it like that, our X. And this could be our Y. So when we graph it here, it would be our Y. This is our X. Okay, so we have each of our values, right? And then the first thing we do, right, is we find the deviation from the mean, right? Because obviously that's what we want. We want to see how far each data point, the objective is to find the standard, right? So kind of like the average deviation from the mean. But because but first we actually have to find what's the deviation from each single point from the mean, okay? And the way we do that is by taking the actual point and then subtracting the mean from it, right? That makes sense, right? Because if this is the mean, if you look at the graph here, if this is the average, the red line, and you can actually see how far away each point, how the deviation, how spread out it is from the mean, each single point, right? So that you see that in green. So I did that. So you do 8 minus 5. So for example, let's look at this one. Where's 8? So the 8 is the first one. So this is 8 here. Let me put that a little bit bigger here. So that's 8. And 8 minus 5, 8 minus the average is 3. So you can see that from 8, 7, 6, 5. So it deviates 3 units from the mean. Okay, and I did that for every single data point. I did 8 minus 5, 7 minus 5, 1 minus 5, and I put the numbers here in green. I also labeled the dotted line as the actual distance, right? Now, because distance cannot be negative, for example, if you look at the fourth point, you see that actually it's supposed to be at 7. Oh wait, no. Excuse me. I mean the third one. Here, the third point. It's actually at 3, but it's lower than the actual average, and so we have a negative answer, which is -2. So it's -2, right? But distance cannot be negative. And so that's why you have to take the total square deviation. But before that, this guy in this video, he actually took the total absolute deviation, which we're going to talk about in a second of what it actually means. So the total absolute deviation is basically the absolute value of what we did here. So I took the absolute value, basically just these numbers. So basically these numbers without the negative. So that's 3, 2, 4. This is -4 becomes 4, -2 becomes 2, etc. I added it up, I took the sum, and it was 14, which makes intuitive sense. That's the interpretation of total absolute deviation. It makes intuitive sense. Not the interpretation, the benefit. So it makes sense because it's literally all these green lines or all these numbers added up as a distance. So it's not distance, it would become, is it displacement? No, we're not in physics class. Total distance. Yes, it's the total distance, right? This is the total distance the total distance, yeah. So it's basically all these green lines or all these green numbers added up together, which makes intuitive sense. You could see it graphically. It makes graphical sense and visual sense. Now, the total square deviation, on the other hand, makes a little bit, it makes a lot of sense. So we did this, right? That was our deviation from the mean in accordance to every point. And then we took the total absolute deviation. And now that we took the total absolute deviation, we can square them. Well, we don't really need this at all. Like, you can literally just cover this and do the entire problem and find the standard deviation without finding the total absolute deviation. Because all you have to do is just square these numbers, which is super easy to do without finding without actually doing this. So you could have just gone from here to here. So square them, right? So you take this and you square it. So 3 squared is 9, 2 squared is 4, -4 squared is 16, and so on. Now this is the total square deviation. We'll get to this in a second. But when you add them, right, so now that you have the total square deviation, which is all of this squared, now you have to take the sum of that. So the sum is this orange here. So the sum is 38. Now once you have 38, what you do is you divide it by the number of actual data values that you have, which is 6. You have 6 dogs. So 38 divided by 6, you get 2.50, you actually get 6.33. So that's the variance. The standard deviation is the square root of the variance, which is, here the square root is 2.51. So the standard deviation is 251. So each, so kind of, I don't know if it's good to say it this way. So is it another way for saying like the average deviation, like how far each data point on an average deviates from the mean would be 251 units or 251 toys in this sense? Because, yeah. So I thought of it as this way, like it makes sense that you would square root it. Well, no. Because variance is the variability of the data set, the variability of the toys, which is just this stuff without the square root. So what's the difference between variance and standard deviation? Because I know it's about to get the units, because you would square it, so you square it to get rid of the negatives, right? Because you can't add them up, because sometimes it's going to be 0, and if you do that, that's the MAD, that's mean absolute, what is it called? Deviation. So that would be 3 plus 2, which is 5. 5 minus 4 is 1. 1 minus -2 is -1. Then -1, this is 1, and then 1, is that a negative? Minus 1 would be -2. -2 divided by 7. I don't think that works. Yeah, no, that doesn't work. Hold on. Let's do this again. -4, -5, -6, -7. Minus 2 is -5. -3. -3 minus 3 is 0. There. So if we were to do the actual average, it would actually end up being 0 over 6, and that doesn't work. So because of this, we had to take the squared deviation, square it, but that distorts the number, right? Because it doesn't make intuitive sense. Like, you can't really see it. I actually put the numbers here on the right side. It doesn't really make sense. Like, okay, what does 16 make sense, like, visually? It doesn't really make sense. So I think that's why we square root it at the end, because to undo a square, you have to square root. And I think that's why we square root, to get back to the units that we were working in the beginning. So I think if we were to leave it as variance, so in this case, it would have been 6.33 toys squared. I guess that would be, wouldn't it mean the same thing then? Because now this is 2.5 just toys as a standard deviation. So there is a standard deviation of 2.51 units. Now that doesn't make sense. Toys doesn't make sense. You mean units, so like units from each data set. No, toys does make sense, because we're looking at the variability of toys and how each data set has a certain amount of toys farther or closer to the average. So right, this would make sense. 2.51 toys. So about, I'm gonna say 3. I'm gonna really, just to speak, so 3 toys of standard deviation. So from each data point, there's going to be an average of 3. There's a more likely average of 3 toys deviation from the mean. Does that make sense? Or is that what it is? I don't know. But then, okay, but to analyze the actual standard deviation, it's actually a low standard deviation. So it actually looks like this, which makes this data set or any analysis that we do with the actual average more accurate than if we were to have a high standard deviation and we were to make analysis with the average. I think that's my opinion. So I think if we were to make analysis with this average by itself, it would be more accurate because it has a low standard deviation. So the average is really, really accurate to what the data points where the data points are going to be located. While if it had a high standard deviation, the data might be a little bit more variable and might be a little bit more increasing probability that it's not going to be exactly where it should be. It could be a little bit over here, like there's more probability of it being more spread out. So I think that's one benefit of finding whether it's a low or high standard deviation. And then also, when watching like this guy's video, also notice that I got the actual application from the video I watched today, which I'm going to link it in the Google Drive folder, but the actual data I got from another video that I watched yesterday. I got those numbers from yesterday, and then I just watched this guy's video on another data set, and I just applied what he did with that data set to this data set. But he also said something about how the total square deviation punishes outliers, and he showed a little example, but I don't really understand. So I'm gonna have to look into that because it's squared. I don't even know. And then he mentioned Ronald Fisher, who